Hello.
Hello, hi. Is the audio clear?
Yes, yes, it's fine, sir.
Great. Okay, excellent. So thank you for the introduction. I'll just start. So I'm sure a lot of you have a lot of questions, and I hope by the end of this webinar that I'm able to answer all of them. So please post any questions you have in the question and answer box, and I'll try and answer as many as possible. So first of all, I want to say I hope all of you are safe and that you haven't been affected by the COVID-19 situation. I'd like to thank all the people working hard around the clock and around the world, serving others who are struggling with this illness. You're truly an inspiration to all of us. So let's share some facts about Amrita first. So Amrita University is very unique in that it's only 16 years old. We're ranked amongst the top Indian universities as per NIRF and International University rankings. Of the 900 plus universities in India, we are ranked 8th. Amongst private universities in India, Amrita is ranked number 1 by the THE International Ranking Agency for both an overall university point of view and for engineering and technology subject-wise ranking. So before I begin, I really want to know how many of you thought to yourselves during classes, when will I ever use this concept again? Calculus, geometry? Does the real world actually use such principles? And my answer to this question is very simply, of course. And I hope by the end of this webinar, you have a good understanding of how mathematics works in the real world, and it's important for various engineering concepts. The subject of mathematics is something very close to my heart, and I spent many years studying mathematical theories and applying them to real-life applications. My PhD, for example, was on finding ways to reduce turbulence over aeroplanes. Now, a lot of you must be thinking, isn't this an engineering problem or a physics problem? And the answer is yes. These are questions engineers study, but not without having a deep understanding of the mathematical concepts being utilized, as you'll see in this upcoming webinar. So, the first topic in today's webinar is the exponential function. And what exactly is the exponential function? How did someone come up with that exponential e to the 1 is 2.718? Seems entirely random, right? This large number is 2.718. How did that come out? And I'm sure a lot of you had this thought while you were studying in high school. Who came up with the idea that pi is 3.142, a forever recurring number? Well, in actual fact, this number is actually written in the code of the universe. It's written so deeply in nature. And I'm going to show you where it comes from using knowledge you've already had from school. So when you hear the word exponential, I'm sure a lot of you are hearing this word right now, considering the situation going on in the world. But what usually follows from this? What? You usually hear exponential growth or exponential decay. And, well, there's a very specific kind of exponential growth. And it comes from this formula that I've written here for you on the right-hand side. You know, this graph here is an example of exponential growth. As time increases, so does population size. But exponential growth doesn't actually mean something that grows very fast, as people believe it to mean. It's a particular kind of growth. If you think of the polynomials x squared, x cubed, even x to the 300, these grow faster, right? X squared goes faster than x cubed goes faster than x 300 goes faster than all of them. If I take a number, 3 to the power of 300, that's much bigger than 3 to the power of 2. But none of them are as fast as exponential growth. The most common use of exponential growth is population. The larger population, the faster it can grow. Like rabbits. the more rabbits there are, the more they can reproduce. And this is something that's actually happened with money, right? The more money you have, the more interest you make, therefore leading to more money. So what is the difference between the two? Well, the exponential growth is proportional to how big something is. So the bigger it gets, the more crazy the number grows. So let's look at a particular example. I want to look at a particular example of a banking situation. Now let's say you have 1 rupee, and suppose that the bank gives you 100% interest. Now this sounds very generous, right? But in the real world, it's not that unusual. If you think about rabbits, they essentially double. And it doesn't take a year to do so. So let's consider 1 year with 100% interest. So if I have 1 rupee with 100% interest, it becomes 2 rupees. Now, as you may know, banks don't really wait till the end of the year to pay you the extra rupee. They're actually concentrating, calculating interest constantly. And the more interest they calculate, the more money you receive as a person. So suppose instead of a whole year, they do it twice a year. And this is the equation I have for you here. And I'm still getting 100% interest per annum. So what you end up with is 2.25. Now, again, I had 2 rupees, now I'm getting 2.25. So the bank says, let's go even further. Instead of doing it twice a year, let's do it every month. 2.61. Now let's calculate the interest every day. Every day leads you to 2.71, and actually there's more decimal points. It's 2.71, 4, 5, 6, 7, recurrent forever. What's going on here? This number, the more that I break down the interest into more frequent intervals, the more money I'm getting. I'm going from 2 to 2.25 to 2.61 to 2.71. And actually, when I go even further, let's say that I do it every day for every minute. There's a small typo in the slide. This should be a 60, of course. There's 365 days in a year, times 60 minutes, times 24 hours. That gets me 2.71827. See the difference between 2.71 and 2.718? And now what mathematicians actually do is they say, well, all these numbers are arbitrary. They don't really mean anything. I can forever increase these numbers. Instead of 365 times 6 times 24, I can make it a trillion. I can make it a billion. And I want to see what that number is. And what they see is that this number starts to converge very specifically to 2.71827, and so forth. And actually we call this in mathematics a limit. You can't actually do this calculation because you can't really know what infinity is. It's just a concept. But we can keep on getting closer and closer and closer with larger numbers. And eventually what happens is this: we start to converge. As you can see here, from 365, when I switched it from every day to every minute, my number increased from 2.71 to 2.71827. And again, if I increased it, it would become 2.71827, some more decimal points. So this number comes from a structure that actually exists in nature, namely how things grow when they grow in relation to their size. Or if you like, how things decay when they decay with their own size. Temperature is another example. The hotter something is, the faster it loses temperature. So this number is not just the study of growth, it's the number of proportionalities. Proportion of growth, proportional decay. That's why it's so important. This number actually exists in reality. If we look at the COVID-19 situation in the world, we can clearly see that the number of affected people is growing exponentially. the more people are in contact with the virus, the faster it grows. Just as the more money you have in your bank account, the more interest you accumulate. Let's move on to another topic. Exponential numbers is a fascinating number. And I want to move on to another number that's also fascinating and extremely relevant to engineering. And not just engineering, but computer science. Complex numbers. So here I have a sort of pseudo insult about complex numbers. Maybe some of you understand it, maybe some of you don't. My first question is you might be thinking, well, who cares about complex numbers? You've heard about them in movies, you've heard about people talking about them in high school, you've probably seen them on the internet, but why should you care? Most people go through their entire lives not knowing anything about complex numbers. They have no knowledge. And what it turns out to be is there's plenty of beautiful mathematics with the concept and application of complex numbers. But again, you're all just high school students. Are you ever going to use them? And the answer is yes. As future university students, you will be using them. As future scholars of engineering or computer scientists, you'll be so interested to know that complex numbers feed directly into your lines of work. So before I actually start looking at complex numbers, I want to look at some particular family of numbers. So you've definitely all seen these types of numbers before. We have various things in mathematics, different groups or different sets of numbers. And the first one is the natural numbers. These numbers are what you would think of from 0 to infinity. The next set of numbers after that are integers. Integers ranging from minus infinity to infinity. Like I've written here, -3, -2, -1, and so on. The set of numbers after that is called rational numbers. These are sort of the fractions that you get. That's what I have here. You have -1/2, -1/3, -1/4, all the way up to the largest possible fraction that you could have. Okay? The real numbers are all of the combined above. So the real numbers is just a set of everything. Natural numbers, integers, rational numbers, even something I don't talk about, irrational numbers. Irrational numbers are stuff like pi, complex numbers. Sorry, irrational numbers are things like pi, exponential, numbers that you can't write as a fraction. So the next set of numbers is what I really want to talk about, complex numbers. And in order to look at complex numbers, the thing that we really have to look at is, sorry, just bear with me. It seems that my camera has not been switched on. So I just want to put the camera on. Hi, hope you're able to see me now. Sorry about that.
Okay.
Yep, okay. So what I want to talk about is the complex numbers. Where were we? I was just giving a set of all the different numbers. So I want to show you this quadratic equation, something that you've all seen before. I know you've seen it before. X squared plus 5x plus 6 equals 0. Now there's many different ways to solve this quadratic equation, right? You can use completing the square, you can use factorization, and you can use the quadratic formula. So what I really want to talk about is how do complex numbers arrive in nature? Before I even go into the discussion of why we even use them. So the first thing here is, on the right-hand side, I have this quadratic formula. And I'm going to use this polynomial and solve it. So when you solve this problem, you end up with solutions -3 and -2. Two real numbers come out of the quadratic formula. Now, isn't this bizarre? It's extremely weird to me that two real numbers come out of a formula that has a third, has a square root. Square roots aren't considered to be integers. Two integers came out. Square roots are usually considered to be irrational numbers. Square root of 2, I can't write that as a normal number. It's a forever recurring set of digits. I get a completely rational number from a formula that has square roots. Somehow the square root just disappears. Interesting. How about cubics? Instead of using a quadratic formula, how about cubics? Did anybody actually know that when you're solving cubics, there was a famous cubic equation? Here it is. Horrible. It's very similar to the quadratic equation. We have square roots, we have these A, B, C, D's, except it's much worse. And actually, it takes a whole page to write this out. These dot, 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 dots. There's extra formulas there which I didn't want to write. I'm just giving an example of these formulas. But inside this equation, there's a negative value. Interesting. Inside the cubic formula, there is a negative sign. And there's a square root expression just like the cubic formula. So you would think that when you're solving this equation, a cubic equation, you should end up with a negative in the square root. Seems entirely weird. Why do these equations have negatives in them, in square roots, which isn't possible because you can't take a negative of a square root? And how does an irrational number go to a rational number? Let's look at a problem. I had the x cubed minus x is equals 0. So I'm going to solve this very simply. I factorize it. I factorize out the x, and I have x times x squared minus 1. And then I would break the x squared minus 1 into two brackets, x plus 1 and x minus. Now, obviously, when you solve this equation, you get three solutions. You get x is equal to 0, x is equal to 1, and x is equal to minus 1. It has three roots, and they are real roots. But in order to get these real roots, if you wanted to use the formula, you would have to deal with negative values of the square root, right? If I applied my formula here, I would need to have negative square root values, which means you would get non-real numbers. So somehow, putting in non-real numbers into this formula somehow arrives at me with real roots. In the same way that irrational numbers appear in the quadratic formula, and we arrive at rational solutions. This is a very strange idea. And it gets at why numbers have the names they do. Remember just a few minutes ago, I gave those family of numbers. The important thing I want you to notice is that we know what rational numbers are. But outside of these, there are not rational numbers. For example, square root of 2. Call them irrational numbers. And outside of that, we also have imaginary. Let's speak about this for a second. If you are a scientist or a mathematician or an engineer, you saw the word irrational. What would that mean to you? Well, it generally means stop being crazy, right? If someone said to me I'm being irrational, they're telling me that I'm not making any sense. And the whole point that this word means is here in these examples are, these numbers don't make sense. We have to put them in our formula though, like some form of life hack to make the formula work. Let's have a side note for a second. I'll come back to complex numbers. I want to go back. I want to look at Fibonacci numbers, right? It's a cool example. So you must have all heard about Fibonacci numbers before. You start off with two numbers, 1 and 1, and then you consecutively add them in the sequence. So the first Fibonacci number is 1, and the second Fibonacci number is 1, the third Fibonacci number is 2, and the fourth Fibonacci is 2 plus 1, which is 3, and you continue onwards adding the sequence. and you get a forever recurring sum. And this is what we call a recursive sequence, right? And you may all know that recursive formulas have an nth term. So this is the nth term of the Fibonacci sequence. Now, again, something extremely crazy. I have the square root of 5 in this formula, an irrational number. The square root of 5 has no simple way of writing it. It goes on forever. But yet, somehow, in this formula, when I apply my values of n, I end up with simple integers, or simple real numbers. Isn't that bizarre? These square root of 5, they all just disappear. There's no square roots remaining. But I need them here to make my formula work. And that's why these numbers, when you negatives in the square root signs, they are called imaginary. In fact, the people who are experts in this field call them fictitious numbers. They're numbers that aren't really there, but we need to stick them into formulas so they actually work. So again, it's just another case of they exist in nature. So I guess the question you're asking is who is interested in making formulas for numbers that didn't exist? Now, I would implore you to do some research on this yourself. But actually, it's really funny. There was a whole bunch of Italian mathematicians. And there's one Italian mathematician you can really look into. His name is Cardano. This was around the 1500s, the 16th century. And the reason this is such a big deal for them was because in the Italian mathematical world, if you were an associate professor in mathematics at a university, the way that you would apply for a job would be so crazy, you wouldn't believe it. If you strongly believed you were a strong mathematician and you could take the job of another professor, you challenge that person who had that job to a duel. Right? Funny. You'd fight this person essentially. It's not really a conventional duel though. They had mathematics duels. They would say, I am better at mathematics than you are, and I'm going to give you 10 questions, and I know the answers to them. And you will give me 10 questions, and I'll answer them faster and better than you can answer my 10 questions. And so to win a duel, these mathematicians, they started doing a mathematical arms race. For a long time, they only believed that quadratic equations could only be solved, and not cubics. So if I'm an Italian mathematician and I came up with a cubic formula, I'd have a secret weapon that could shoot anybody down. I could essentially give another mathematics professor 10 cubic equations, and he couldn't solve them. But I can, so that makes me better at mathematics. They were so interested in coming up with these equations that were so hard to solve that they really pushed hard into this area and forced themselves to deal with numbers so they could take somebody else's job. So just as a side note, the quadratic formula, for example, the cubic formula, and all these other equations you see, did you ever think why they don't have any names? Like the Pythagoras theorem. We know that's named after Pythagoras. But why all these other equations, like the area of a circle, the volume of a sphere, the perimeter of a rectangle? Why do they not have names for the people who discovered their formulas? Well, one of the reasons is because we don't know who came up with the results. Instead of mathematicians publishing their works, they kept it a secret because it's their secret weapon. They would discover it, win all of their mathematical duels, but then they would take their secrets to the grave, and someone decades later would rediscover the concept. So the question I really wanted to answer was, why did they even want to go to complex numbers? And the answer is they didn't. They really did not want to study these fictitious numbers. But they were forced to win mathematical duels so they can keep living in the society that they were in. They wanted to continually develop their weapons to keep their jobs. And they were forced to study the theory of imaginary numbers. So obviously I've just given you this brief background history on this mathematical complex numbers. But the main question you're all interested in is how does this actually apply to the real world? And believe it or not, imaginary numbers are so commonly used in engineering. They are widely used in fluid mechanics, the study of fluid flow past an object. They are widely used in electrical engineering. And what actually happens in the real world applications when you're trying to solve problems is imaginary numbers allow us to move from a very real complex system to a very simple problem in what we call the imaginary plane. And what you might have seen is in your classes, you draw a straight line, right, in the X and Y plane. Sometimes you have such difficult problems to solve in the real plane that they're actually infinitely easier to solve in the complex plane. You may have heard something like Fourier transforms before. Fourier transforms reduce a problem down to a simpler one using complex numbers. I have a picture of the movie Wrath of Khan here. Well, actually, interestingly enough, movie industry fellows use complex numbers in a field called chaos theory to produce beautiful planets or galaxies in science fiction movies. Star Trek Wrath of Khan is just an example of such a movie. So they're using these numbers that exist in nature, that were forced to come out of a formula to solve a real problem, to create something what we deem beautiful in a movie. Let me show you a quick example. In fluid mechanics, what I have here is I have a fence of height h in the real plane, x and y, and I have a fluid flow going towards this fence. So let's imagine it's sort of like a dam, and you have water hitting across the wall of a dam. What fluid mechanics are interested in is what is the velocity of this flow, but what is the pressure acting on this fence or this dam? That's the most interesting thing. So actually in the real plane, in the x and y coordinates, this is a very difficult problem to solve. So what mathematicians do, what engineers do is they use complex numbers. And they can transform this problem into a much simpler one. This right-hand side fence can be reduced and broken down to a straight line in the complex plane. And now I can solve the simpler problem and determine the pressure, because I can find the pressure in the complex plane, and then I can transform it back into the real plane. Okay? Another thing I'd like to discuss with all of you is calculus. So we've talked about lots of different things so far, and a lot of this webinar is for an understanding of how mathematics actually comes in the real world, right? And we talked about this exponential number, this beauty of a number that just occurs from this interest rate formula by just keeping on increasing the value of it. Then I showed you how complex numbers come in from a real world problem. So I'm going to talk about calculus. And you're probably thinking at this stage, oh God, why? I've had enough of calculus. So we've handed in all of our final exams for high school. We're ready to start college. I don't want to talk about calculus anymore. But actually, in my experience, I feel as if high school students, and not just high school students, some university students, they don't actually understand what the real importance of calculus is. So I want you to come from this from a blank slate. For now, forget everything you know about calculus. The biggest danger to approach a subject like calculus is to think about it as a set of rules that you just memorize, and you just apply them to a bunch of examples. If that's how you've been approaching calculus so far, well, it's not the right way, to tell you the truth. It's not even funny that that's just how basic the concept of calculus is. The design and use of calculus is such a creative process, and to just bundle it into a set of rules is a shame for the subject. So calculus is actually an abbreviation for something called infinitesimal calculus. And I know that doesn't reel off the tongue so nicely, infinitesimal calculus. So they shortened it to calculus. Now, we have many branches in mathematics, right? Many different subject areas. Calculus is just one of them. But each one of these subject areas is keyed into a single big idea. Take geometry, for example. Geometry is about the subject of structure of shapes and objects. Algebra is the study of relationships and their relationships with one another. And probability is about chance. So each subject of mathematics has a specific big idea. So what about calculus? Well, calculus is the study of change. Okay? Calculus was developed independently by two famous mathematicians. And there's actually a huge argument in the academic world about who invented it. You know, mathematics is never invented. It's actually there in nature. It's mathematics that happens here on this planet happens on Mars or Pluto or Neptune. Mathematics doesn't change. The physics that we apply to it is different, of course. The gravity on Mars is different from the gravity on Earth. But the underlying equations we use to solve such problems remain the same. So there's actually two people. Everybody heard of Isaac Newton, the English fellow, the apple fell from the tree. But the other gentleman was Gottfried Leibniz, famous German mathematician, not as famous as Isaac Newton, unfortunately. But both of these fellows somehow developed simultaneously this big idea of calculus. Now, you may have all heard of Isaac Newton's famous story, right? He was sitting under a tree and an apple fell on his head or on the ground next to him. So this story is, of course, up to debate whether the apple fell on his head or if it fell next to him. But when this apple fell, Newton, sitting under this tree, thought to himself, okay, gravity makes the apple fall, right? Everything just falls. And he watched as the apple falls. He thought that the moon, way up there, the sun, up in the sky, is being held in place by gravity, but it doesn't fall to the earth. So he thought, how does this work out? How can an object such as the moon stay in place even though it has gravity acting upon it, but an apple just falls? So he tried to solve this problem. And of course, he didn't know how to solve this problem. And he ran through many big problems. Gravity is something rather unusual, right? Gravity, like most forces, are what we say inversely proportional to the force it exerts on something. So if you look at this graph here, as your distance increases, the force of gravity gets smaller and smaller. Now here's the actual problem. Newton was trying to work out how the force of gravity relates to distance. How does gravity change over distance, right? That's the real problem we're trying to solve here. And this is tricky because, as you can see in this graph, there is different behaviors at every place you look. Now, let's compare this to a straight line. If you want to know how a straight line is changing, that's not really hard to calculate. You just need to compare 2 points in a straight line, and you've all seen this in your mathematics classes before. If you have 2 points on a line, you can just compare how much it changes from one quantity compared to another. And we get them as a ratio. And this ratio is known as a gradient, right? If I take 2 points, x1 by 1 and x2 by 2, I can calculate the gradient, this steepness, by dividing the change in y over the change in x. But in Newton's case, there's a problem. For any curve that grows exponentially, or proportionally, or inversely proportionally, no matter which 2 points you take, you're always going to get a different value for a gradient. And the reason our approach for a straight line works is because it grows linearly. You could choose any 2 points on this line, and you will always get the same gradient. It's growing at the constant rate. hence the term linear. So what did Newton do? He has this big problem. Gravity doesn't grow as a straight line, it's inversely proportional. How can he calculate at the exact point that he's interested in what the gradient is? So he thinks to himself, and he's a very intelligent fellow, he thinks, okay, right, this is the problem we're trying to solve. I have a proportional graph, and I'm trying to calculate what we call the tangent to this point. He says, let's think about a circle, okay? What he really wants to know is how much is really changing at a given point. Now, you should already know that the gradient in terms of geometry is the steepness. And if you have the steepness at a given point, then that's its gradient. So what Newton was really interested in is what we call the tangent to the graph. He wants to know the gradient at a very specific point. But there's a problem there. The problem is that in order to determine a line, tangent, to a graph, you need 2 points. And here, well, actually, we only have 1 point. So how can I determine how this straight line behaves with just a single point? So here's what they both did. They said, okay, I don't know how my graph is behaving as a tangent to a point. So let's go to a problem that I already know how to solve. And this is what everybody does. They go to a normal problem. So they both look at the circle again. And they draw a tangent along the circle. And the tangent meets at 1 point. But then what do they do afterwards is they draw a whole bunch of parallel lines in this circle. Okay? Now, these lines, they're called secants, right? You have a straight line through a circle, they're called secants for seconds. Now, these lines, they have 2 intersecting points with the circle. All of them have 2 intersecting points. But this one only has 1. So what they both do is they say, well, we're interested in the length of this line. We're interested in the chord between these 2 points. And what happens if you have a circle and you draw a parallel line and you calculate the chord, and then I move closer to the edge of the circle and I draw a parallel line and look at the length of the chord, and you keep going, you can see that the length of the chord actually reduces. And it keeps reducing, reducing, reducing until you get to this specific point where the length of the chord is 0. So Newton thought, what if I can imagine this in the same case of graph? So what he does is he takes his inversely proportional graph and he draws a secant into the graph. Now he says this graph has 2 points of intersection. The first point of intersection he'll call x. The second point of intersection he doesn't really know, but it's some distance away from x. We call that delta x, right? And you may have seen this in your physics classes, x plus delta x. This just means a small distance away from x. Now when you're looking for the value of y, well, y is a function of x. So the corresponding value of y is just going to be f of x and f of x plus delta x. And how do you work out the gradient of a straight line? Well, you take the 2 points and you calculate the ratio. So you would get f of x plus delta x minus f of x over x plus delta x minus x. Well, that gives you this straight line. And that's not what he's interested in. What Newton was interested in was the line of the tangent. So then he thinks, well, I know how to calculate this length of this line here. And I know that if I slowly move the line down, 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 the value of this length is going to decrease until I can get to a tiny point on the curve. So what he does is he says, what am I trying to do is, I'm trying to bring this distance between x and x plus delta x smaller and smaller. So for convenience, And to avoid all this horrible notation, he says, instead of calling it x plus delta x, I'm going to call the difference delta x h. This is the difference between the two. And he said, I'm interested in when this difference gets closer and closer to zero. The definition of limit comes in. So he said, I can calculate the point on any curve, gradient of any curve, by looking at the gradient at a point of the curve and seeing how that behaves as I get closer and closer to zero. Very interesting idea. But let's look at something more interesting to your taste, right? I've talked about calculus now, and I've talked about how this really works in the real world, right? It's not just a bunch of formulas. Let's look at an office example. Not just an office, like a school or a house, anything. Let's say on a given day, the temperature in an office building is maintained at 25 degrees. And the heating in this building is shut off around 10 p.m. And the heating automatically turns on at 6 a.m. Now, on a particular day, the temperature inside the building at 2 a.m. is found to be 20 degrees. And the outside temperature was 5 degrees at 10 p.m. And this has dropped from -5. And what we're interested in is what is the actual temperature in the office at 6 a.m. before the heating comes on. So I know this sounds like a very complex problem, but actually it's not that difficult to think about. You have the temperature outside the building and the temperature inside. And obviously as time goes on, the temperature outside will increase and then decrease again. And the temperature inside the building must maintain constant for all the people working in the building. And actually this problem can be modeled using calculus. It can be modeled using these curves and tangents. And you can find out at a specific time of day, what is the temperature inside the building. Okay? So what we do is, when we start thinking about our problem, I have the temperature inside the building, and I'll call that capital T. And I have the temperature or outside the building, the surrounding area, and I call that TA. Now, in physics, or even if you think about the real world, the temperature inside of a building is affected by the temperature outside, right? If it's hot outside, it's going to be hot inside your building. If it's cold outside, it's going to get colder inside your building. So we're looking at the temperature of coldness because it's the winter. So the temperature inside your building minus the temperature outside. But what I'm interested in is how this changes over time. And this is where calculus comes in, because calculus is the rate of change. So what you have is the temperature of the building, capital T, over time itself. And these things are what we call directionally proportional, right? There's a direct relationship between the temperature outside the building and the temperature inside. As the temperature outside increases, the temperature inside increases. So this directly proportional gives us this constant K. So now I can solve this problem using all the calculus rules that you have and find out at a specific time what the temperature will be inside the building, given that I know what the temperature outside will be. This is known as a modeling problem. And these are the type of things you use calculus for, not just for solving the temperature inside of a building. We're determining how fast a plane will go under certain aircraft conditions, determining what the pressure of the water will be for a submarine to glide through the water. All of these calculus, exponential, imaginary numbers, they all come back into solving real-life problems. Okay? You're all using these concepts without knowing that they exist. So I know I've looked at a lot of heavy mathematics, so I'm going to look at something a little bit more lighthearted. I'm going to look at something called graph theory. Now I know you're all thinking, oh, he's going to draw these horrible graphs and we're going to think about how they intersect and all these kind of things. Well, actually, It's not the type of graphs I'm talking about. The type of graphs I want to actually look something like this. Now you're thinking, how is this a graph? Well, a graph is just a bunch of straight lines, right? Well, all I've done is drawn a bunch of straight lines and they're connected by specific nodes. And each one of these nodes has a edge. The edge from A to B is 6, A to D is 1, and so forth. These type of graphs are used in everyday applications. They're used in network applications. They're used in electrical engineering. They're used for businessmen. Businessmen, when they go to work, they want to sell you a product. They have a map. They're going to start at their house A. They have to return to their house A. So they want to maximize all the places they want to travel to. This is called the traveling salesman problem. But they want to do it in the shortest distance, right? They want to travel from A to Z and return home to A by 5 p.m. But they want to maximize the number of houses they can go to. And this is what the subject of graph theory is. And there are so many different types of algorithms out there to find the shortest distances. But I want to look at one specific use case. Let's look at this graph here. Now let's think about your situation here at home. And let's take A to be your house. You know, and B is your friend's house, and C is a shop, and I don't know, D is school, and E is the chai shop. And the idea is you want to travel from A to C in the shortest possible way. Now, this is a very simple graph, and in the real world, you have these huge networks, huge networks. Think about the internet, right? I'm connected right now. So all of them. And the internet connection is the fastest, shortest way to get from my computer to the server to your computer, right? And then pass the information back. It can't go a long-winded way because otherwise you'll never get the information in the fastest amount of time. But how do they do that? There must be various algorithms out there, right? And engineers and mathematicians, they spend so much time trying to figure out the fastest way to solve a problem. What's the fastest way I can get electricity, right? You've all studied circuit diagrams before. Well, that's just a graph. I'm just trying to get electricity from one point to another point. But what is the quickest way to do that? Mathematicians are always doing this. Engineers are always doing this. They're trying to come up with new ways to find the fastest way to do something. Let's look at this example. Okay? I start from point A. And we draw this nice table on the left-hand side. Now, obviously, if I'm already at point A, I don't have anywhere to travel. So the distance from A to A is 0. Now, the distance from A to B, you believe is 6, right? And if you think about this in terms of a map, let's say my school is here and my shop is here, right? My school or my house is here. And I can travel in a straight line. That may not necessarily be the fastest way. Google has many different ways on the GPS to show you how to get to a location, right? Well, fastest way from A to B would actually be going from A to D and D to B. That would only take me 3 minutes instead of 6. So I found the fast way to B. The fastest way to D, of course, is only 1 minute. The fastest way to E would be 2 minutes. But if you have a complex system, a huge graph, a huge network of, I don't know, 500 nodes, 900 nodes, 10,000 nodes, right? You think about a WhatsApp group. A WhatsApp group may have 256 people. You have to send a message to 256 people at the same time in the fastest possible way. It's all using graph theory, all using these algorithms to find the fastest way to get somewhere. But how useful is it? How useful is this? You know, and I talked about that people have used it in terms of the internet and electrical situations. Well, Google's GPS uses graph theory, tells you the fastest way home. The famous traveling salesman problem uses shortest distance algorithms so you can maximize his sales in a day. You can go home and keep his family happy. Oh, I sold 10 butters today. I sold 20 vacuum cleaners. You know, I hit all these homes. But what about our current situation in the world? Right now, we're all suffering from being in self-isolation because of COVID-19. Did anybody ever think about how we could use graph theory in this situation? Actually, some people have, and actually some countries did. What some countries did is they used the location tracker on your phone to determine who you're coming in contact with. If I have my phone A, my phone B, this is my friend, this is my father, and the locations are both on, my father and me come in contact with one another, and we realize that the location tracker realizes that we come into contact with one another, and that's stored somewhere. And what these governments have done around the world is they said, well, person A was tested positive for coronavirus, and person B has now come into contact with person A. And now they're going to track person B with his GPS location and find the shortest distance so they can apprehend him and put him in self-isolation. Fascinating, right? That's what they've been doing. That's what some countries have been doing. Some countries that have low numbers, they've been using your information to determine which way to stop the virus from spreading by using graphing. Such a simple idea of finding the shortest path has been used in real-life applications. And I hope you're slowly understanding why mathematics is important to the real world. Why your teachers have you learn this theory, these equations. And you may not be using them right now, but the whole world surrounding you is using them at a constant rate. And this talk right now is only happening because the underlying electrical and network systems in the computer and the internet provided by the network provider, both using principles of calculus, both using principles of graph theory. It seems so interesting. You would learn all these concepts and theorems, but no one's ever told you the applications of them. You know, I had a mathematics professor once. He was so fascinating. He was always on the side with students. And one particular day, and he would assign all of the college examinations, right? So you can imagine we're a college of 500 different courses, and all the exams happen at the same time. And he was like, how do I schedule the examinations in such a way that one student doesn't have to take two exams in the same day? What can I do? How can I maximize their learning process, minimize their stress? So he said, I know, let's draw a graph. Let's use graph theory. And that's what he did. He took all the possible courses across the whole college. And he said, okay, student, for example, myself, is studying mathematics and physics. And he's also studying fluid mechanics. Those two exams can't be on the same day. So let's have them connected. And then he says, the student is also studying English. So they can't be on the same day. And he plots this huge graph of all the different exams and finds exactly where he can outline all the examinations. Let's look at something a bit different. We looked at calculus, we looked at exponential, we looked at engineering. I want to go into something a little bit different. You know, of course mathematics is important to engineering, of course mathematics is important to computer science. But what about biology? How is mathematics important to biology? Now, at this stage, you must be thinking, well, he's crazy. You know, mathematics is in biology. Biology is the study of nature, like humans or animals. Can it really be used? Are people really using mathematics in biology? Are they really, can they use calculus? The calculus is the change of something. Can they use probability? The probability is the chance of something occurring. Well, of course. Modern day biologists use something called hypothesis testing. You see, biology isn't like mathematics or physics. You can't simply prove something is true in biology. Every human is different. Something that works for me will work differently for you. So what they do is they do something called hypothesis testing. And they have two hypotheses. There is no significant difference in one experiment, and there is a significant difference in the experiment. So what type of experiments do they do? Well, let's say that scientists have found a cure for COVID-19, and I hope that happens soon. Now, their job is to test how effective this vaccine is on a group of people. So they run an experiment. And they would test the group before the cure is given and test the group after the cure is given to see if it was effective. And the statistical analysis, the probability analysis, would then determine with a probability how likely this cure works for a general population. And the nice thing about mathematics and statistics is that you can have a small group, let's say 25 people. And if the cure works for the 25 people for a significant amount, you can extrapolate that data to apply that to the population. The whole population you can use that to. And that's what people do. That's what scientists are doing. But of course, there's so many different cases they have to apply it to. It may only work for males. It may only work for females. It may only work for Indians. It may only work for Americans. They have to look at all these different parameters when they're doing the testing. But they obviously can't test it on billions of people. But they can test it on a small group and then hypothesize with a probability how this actually would work. Another example, back to calculus. Biological modeling using calculus. Now, this is probably one of the most interesting cases, at least for me. Remember how I said calculus is the rate of change? Well, we could use that in biology. We can use the study of the rate of change of a population over a given time, for example. Right? Exponential is a directly or inverse directionally proportional graph of growth. Population is an example of growth. And if I want to know what the timing of the population is at a specific point, I would draw my tangent line and calculate the exact population at a specific time. But it goes even further than that. Biology, we can study the rate of change over time of a population, or the rate of change bacteria cells die when inserting an antibiotic. And if done correctly and in an intelligent way, mathematical modeling can predict exactly how much medicine is required to kill a specific virus or bacteria in a specific amount of time. Did you ever think, when you go to the doctors or hospitals, how they know to give you a specific amount of medicine? Isn't it curious? They just tell you, take this tablet 3 times a day for 5 days. You just think, what? How do they even know that? How do they know that? They just give you a tablet, you don't know what the tablet is. You take it from complete faith that in 5 days' time, after you take this tablet 3 times a day, 15 times, you're going to be cured of your sickness. Well, because somebody already modeled it for them. They know with some probability this drug will work for 95% of the population, 99% of the population. And they know for sure how long the sickness will take to go away with the medicine. Fascinating. I hope I still have your attention in this talk. I hope you're still seeing the importance mathematics plays in all these subjects, in engineering, in physics, in chemistry, in biology. It's not just a bunch of formulas you're forced to learn and memorize. It's a beautiful, ever-growing subject that has a place in nature. Mathematical biology is even being used to synthesize drugs. There's a whole field in mathematics dedicated to find out if one chemical is chiral to another. Because if you can mathematically show that, pharmaceutical companies would save millions, if not billions of dollars, because they don't need to start synthesizing without knowing. They know it exists. The last subject I want to talk about is number theory and cryptography. And sort of these subjects, they come hand in hand. And they're very important, actually. This whole chat right now is using cryptography. Your WhatsApp is using cryptography. All your social media uses cryptography. And they actually all use number theory. So I want you to start thinking, every day, how many of you use all these social media platforms? Facebook, Twitter, Instagram, LinkedIn, YouTube, Google. There's a new app, TikTok, there's Snapchat. You all use social media. If you don't, your parents do. If you're not using it now, you'll be using it when you start work. You'll be using it when you start going to college. But did anybody think about what is baked into these applications? How your pictures are kept secure, how your messages are kept secure from a third party. If I send friend of mine a message. I want it to be private. How is that information kept private during transmission? Well, the answer is cryptography. Cryptography is the study of keeping messages and images secure. And cryptography uses a subject of mathematics, a field of mathematics called number theory. So what exactly is number theory? Well, actually, it's just as what you think it is. It's just a theory of numbers. Number theorists, they study patterns in number systems. They learn how to derive equations to divide numbers, to find the greatest common divisors. They study a very specific group of numbers. But how, you must be thinking, how are these number patterns used in cryptography? Let me show you. We're getting a little bit abstract here, so bear with me. I have two definitions. Two definitions that are widely used in cryptography. First one is divides. We say that an integer A divides B, written A line B, where there's a third integer, C. B is equal to A times C. So that's saying that it's a perfect division. There's no remainder. So 2 would divide 4, because 4 is equal to 2 times 2. 3 divides 9, since 9 is equal to 3 times 3. 2 does not divide 5, because there's no integer C that can make this equation solved. Right? Remember, integers are numbers that aren't fractions. So the next definition is something called congruence, modulo. Now this one is a little bit more difficult to understand, but I guarantee you every day in the real life you're using this concept without fail, every day. You are seeing this modulo arithmetic and you don't even know about it. It's a shame, because it's such an easy concept. Modulo arithmetic is just division with the remainder. We say that A is congruent to B modulo M if M divides B minus A. 13 is congruent to 1 modulo 12 because 13 minus 1 is 12. 12 divides 12. So let's try and understand this a little bit more. Let's look at an everyday example. Time, right? Right now it's 11:35 a.m. Okay? After 11:35 a.m. it becomes 12 p.m. After 12 p.m. I arrive at 13 p.m., right? Now intuitively you all know that 13 p.m. is 1 p.m. 14 is 2 p.m. 20 o'clock is 8 p.m. But why do you know that? It's not like you just memorized that, right? Well, that's because of modular arithmetic. The dial on a clock is from 1 to 12. But even at 13 in the afternoon, it's still at 1. Well, that's because 13 divided by 12 has a remainder of 1. 14 divided by 12 has a remainder of 2. 15 divided by 12 has a remainder of 3. And you can keep going in this cycle, right? 24 divided by 12 has a remainder of 0, which is why at midnight the clock says 0, 0, 0, 0. So you must be thinking, well, that's all fine. I can divide, I can calculate remainders. How is that used for encrypting messages? How do people use dividing numbers to keep my messages safely? That seems so bizarre. So it can't be true. Let me give you another example. What day is it today? Today is Friday, right? Let's label the days of the week, Sunday being 0, Monday being 1, Tuesday being 2, Wednesday being 3, and Friday being 4. Okay, so Saturday would be, Friday being 5 and Saturday would be 6, because Thursday is 4. So if I asked you, if today is Friday, what will the day be in 18 days' time? Right, and a lot of people that just go to their fingers will be like, okay, today is Friday. No, Saturday 1, Sunday 2, Monday 3. No. Very simply, I already labeled the numbers, days of the week, 0 to 6. Right? 7 days in a week, and the possible remainders for 7 are 0 and 6. 0, 1, 2, 3, 4, 5, 6. Today is Friday, is 5. 18 days later, 18 plus 5 is 23. Now, 23 divided by 7 has a remainder of 2, meaning that in 18 days' time, it should be a Tuesday. So simple. And this idea of remainders is used in cryptography. Let's look at Julius Caesar, famous Roman Empire, very famous. He used encryption. He used modular arithmetic to encrypt messages in private communication. How did he do this? Well, Julius Caesar says, I'm going to shift the alphabet. There's 26 letters in the alphabet. Now, the possible remainders of 26 are 0 to 25. So I'll call A 0, B 1, C 2, D 3. I'm going to shift them. That'll be how I scramble up all the messages. So he came up with this formula. X, where X will be the specific position of the letter, plus some jumbling aspect. Modulo 26, meaning that when I add these numbers together, I want the remainder when I divide by 26. That's how it works mathematically. So let's look at an example. H in the alphabet is the 7th letter, math numerically. A is 0, B is 1, C is 2, D is 3, E is 4, H is 7, U is 20. And I'm going to use K as 7. So when I do 7 plus 7, I get 14. 14, letter of the alphabet, would be O. When I take U, U is 20. 20 plus 7 is 27. But remember, my numbers are between 0 and 26, so I want the remainder of 27 when I divide by 26, which is 1. And 1 is mapped to B. So the word help gets mapped to OBSR. And what Julius Caesar would do is, in his private communications, is he would take his message, he would shift the letters at a constant rate, and he would send them across to his army. Attack this wall, defend that fortification. Can you bring me back some cheese? All his private communication was used by his Julius Caesar. But of course, that was 2,000 years ago, right? We've come a long way in 2,000 years. In Julius Caesar's time, there was no computers, right? And in modern day cryptography, something is different. And what cryptographers do now is, instead of using this shifting of letters, they use other fields of mathematics, number theory, that they go very deep in. They use something called prime numbers. A relatively simple idea started in 1976, where famous computer scientists and mathematicians started using prime numbers for encryption. Now, you must have all heard prime numbers before, and they think, why prime numbers? Well, it's because prime numbers are so unique and special. They don't have a pattern. It's hard for an attacker to determine the meaning of private messages because with prime numbers, there's nothing there for them to relate to. They go on forever, and there's no systematic way to determine which one is next. So I hope all of you were able to follow this talk, and your minds have become more aware of the pivotal role mathematics plays in our lives. Here at Amrita University, we not only prepare you with the knowledge of engineering and computer science, but we also give you a strong hands-on approach on how to tackle these problems I discussed. We train all of our students to handle various problems in the world, showing you not only the theory, but the real-life applications. And this is where our Amrita curriculum really shines. Our courses such as designing teach you how to think like research scholars, plus applying that into situations. For example, our faculty here have developed a drone that allows us to transport medical packages to remote areas. They've developed applications on the phone to detect when a landslide may become certain villages, all using the concepts of engineering and mathematics. I think it's time that we switch to the question and answer session, and I'll be answering some of them that you've been posting here. So I'm just going to open up here. What are the basic differences between an IT engineer and a software engineer? It's been posted quite a few times. What is the basic difference between an IT engineer and a software engineer? So I suppose the basic difference is that an IT engineer will be dealing more specifically on computer use cases, where a software engineer will be looking more about the engineering of the actual particular product, right? IT engineering could range from hardware, a lot of hardware analysis, where a software engineer will be looking at the applications of the software. What's the basic, how to prepare mathematics and entrance exams? So please elaborate. I think in order to prepare for mathematics and entrance exams, you need to really stop and think about what is really the question that's being asked here. A lot of the time you'll be forced to learn formulas and theorems and just apply them, and it's not the correct way to understand mathematics. You need to understand how this problem works in a particular situation, right? You know, you have baked into you that when you're solving Pythagoras' theorem, it only works for a right-angled triangle. But you have to think why. Why does Pythagoras' theorem only work for a right-angled triangle? Okay? How is it that when I differentiate an exponential function, it just stays an exponential function, right? What's changing then? And understanding these concepts in mathematics will really help you in terms of your entrance examinations, because the question may change. Tomorrow it could be how do you calculate the tangent of a sine graph, and tomorrow will be how do you calculate the tangent of a cosine graph. But if you don't understand what this concept of tangent is, you'll never be able to apply it in a different situation. Based on which technology does Google map its longest or smallest path for several locations? Well, Google is not very open about their information. Unfortunately, I can't answer that question. They have a huge team of experts where they're studying all of these things all the time. You know, and you may have seen there's now Google Live updates where there may be an accident on the road, and they'll tell you this route has an accident, we suggest you take this route. And that's thanks to us, right? When I'm driving on the road and I'm stuck in traffic for 45 minutes, you know, my brother, for example, he can get my phone and say, there's an accident on this road. Then Google, 10 people may say there's an accident on this road, and Google will be like, okay, there's an accident on this road, let's map a different route. So they have this supercomputer, and they know all the specific points, right? For example, if I'm looking for a petrol station on the way, Google will then remap the location to the shortest distance for me to find a petrol station, and then get me to my location. What are the applications of integrated mathematics and salary? Well, there's actually a lot. Actually, surprisingly, learning mathematics is not just essentially about learning formulas and theorems. It's learning how you approach a situation. At Amrita University, we don't just teach you theorems. We teach you how to think, and that's where industry companies want. They want somebody that we can give somebody a problem to, and they can go outside in the real world and they can solve it very quickly, and they can come back and we can give you another problem. And that's what mathematics trains you to do. That's what engineering trains you to do. It's not that we build a bridge. If I built the same bridge everywhere else, life would be simple. But that's not the case. The Golden Gate Bridge in San Francisco, it's an engineering marvel. The Gherkin and the Shard in London, they're both engineering marvels, but the architects that designed them had a really, really beautiful vision and a beautiful understanding of mathematics. And they were able to construct this lovely building or bridge for people to come and look at. So that's where the applications come in, that level of understanding, a level of being able to think outside of the general box, thinking beyond the rules that you've been taught in school, thinking beyond the concepts that have just been put to you on a plate, and going, well, I know that the derivative of 3x is 3, but why? And then you take that concept and you apply it somewhere else. I'm interested to pursue a math which will be better, pure math or applied. I'll be honest with you, you shouldn't apply at the beginning for pure or applied math. You should come in with an open arms, and you just start your study. You may enjoy pure mathematics, and pure mathematics is this wide range of theories and why things work. There's a whole subject in mathematics in determining how you can warp shapes from one thing to another. For example, in math, I can prove that a coffee cup is the same as a donut. mathematically, right? And that can be used in use cases. They use it in black hole theory that if the shape of a wormhole is one thing, then it can be mapped to a different thing or a different form. But don't put yourself too quickly into a situation of applied or pure. To start studying, start coming to the classes, start getting a good, deep level of understanding of the subjects around you. Don't just accept something the faculty tells you. Challenge them. Ask them, why, sir? Why does this work? Once you have that level of understanding, that deep understanding of subjects and concepts, you really start owning the material around you. How do you think all these actors or movie stars or artists develop new music, new movies, new dances? They understand conceptually what's going on behind each thing. Just as you that you want to become an engineer or a banker or a stock trader, every situation in the world is different. Every day something is changing. Just a month ago, oil was minus $40 US. They were giving you oil, money to take oil. The stockbrokers couldn't have predicted that. A lot of people lost money. But if you had an understanding of the real world situation happening, you could have saved so many people that loss of money, that loss of pain. What algorithms and software do graph theory use? There's so many different algorithms. There's the shortest path algorithm, there's Bellman-Ford algorithm, there's breadth first search, there's depth first search. You can even apply graph theory algorithms for trees. Family trees are basically using graphs. It's such a dense subject area that's being studied every day. Just yesterday, not yesterday, sorry, a few days ago, my little brother, he sent me a paper from Nature, which is using graph theory to look at the spread of COVID-19 growing over time. Such a fascinating thing, using just a simple concept. You have one person, and you're watching how that one person, the virus, can spread across the whole network. It's so fascinating that we use mathematics everywhere in life. But could you please elaborate how mathematics can be used in saving technologies? In what sense do you mean by saving technologies? I mean, I can explain how mathematics is used to save lives. We talked about the mathematical biology. In terms of saving energy, I think in terms of saving energy, I have a friend in the UK, he works in an oil company. He uses mathematics to determine exactly how much oil is needed for a specific aircraft, how much oil is needed, how much fuel is needed for a specific aircraft for a flight. For example, a flight from Emirates to India only needs this much fuel and this much oil. So they'll only supply the plane with this much fuel and this much oil to reduce the pollution in the air. And I think going forward, there may be a situation. Let's say your computer stops working tomorrow. This laptop, this whole electricity can go down, right? But the theory that you developed in school, you should be able to use that still to reconstruct everything, right? Now, mathematics that you learn, you should be able to use in everyday life. When you go to the shop and you see that something's discounted at 20%, you know how to automatically discount a formula, right? Oh, it's 100 rupees and I discounted by 20% and this is how much it costs. So why can't we use that for other use cases? If I know how an electrical system in a laptop works, I should be able to rebuild that system. Okay? What algorithms and software does hypothetical testing?
There is a question.
Yeah.
Yes, there is a question by Sunny. He wanted to know what is the use of mathematics in artificial intelligence and data science.
Oh, wow, that's a great question. Well, actually, artificial intelligence is all mathematics. It's all relationships. Machine learning, also known as artificial intelligence, is relationships between a set of data and another set of data. And what I'm trying to determine is how this set of data behaves. And can I predict how another set of data is going to behave that my algorithm has never seen? And then we use probability and statistics. And we'd say is, what is the probability that I'm able to correctly identify that this is Dr. Kurunandan's handwriting, right? And you would look at all the specific things. I saw recently, someone sent me a paper a year ago, not recently. They were using, you all know what captchas are, right? When you log on to the internet, you have to put in, I'm not a robot. So they were using machine learning, artificial intelligence, by looking at the word and putting a straight line like a tangent across the word and determining all the points of intersection and saying, okay, if I put a straight line here on the letter T, it's just a straight line. So I know that this is the beginning of the letter T. And then I'll draw another line. And okay, I have a gap, a gap, a gap, a gap, a gap. And I now have the letter T. So I know on my capture I have the letter T. Then it looks at the letter C. And it draws a straight line here and it says, okay, there's a curve here. So then I start thinking about all the letters that have a curve. Then I draw another straight line. And I'm like, okay, my point of intersection is I have more curves. And it starts determining with probability in calculus, what is the likelihood this letter is a C? And then it will gather all that data, and it would use artificial intelligence to tell you what the captcha is, therefore breaking the system that Google has implemented to say, well, this is clearly a TCH, that's the captcha. Okay? What algorithms and software does hypothetical testing and biological modeling use? So there's many different types of testing for a hypothesis in biology. There's t-test or chi-squared, there's ANOVA, and it really depends on the experiment you're doing. For example, if I'm just testing how sunflowers grow normally compared to how sunflowers grow in oil, I would use a t-test, and I would just compare the average height of sunflowers normally as opposed to how the sunflowers have been growing in oil. And I would determine a relationship and see if the average height has changed over time. But if I want to, say, for example, take two variables, let's say a tennis ball, and I want to know if a tennis ball is going to bounce better if it's been in the freezer at a specific temperature or put in the hot air. So now I have two variables, right? But I can go even further and talk about the brand of the tennis ball. So does the brand of the tennis ball and the temperature the tennis ball is kept in affect how bouncy the tennis ball will be? Right? Because these Wimbledon players, they want to know what the best ball to use is at a specific day of the year. So it's fascinating that we use mathematics everywhere in real life, but could you please elaborate how much mathematics? I just answered this question. Give one example of biological modeling. Well, we gave an example of the vaccines, right? What's an example of the vaccines? Oh, but that was hypothesis testing. Okay. Example of biological model. Let's say I have an antibody. Let's say I have a cell, right? I have a healthy cell, and I know how this cell behaves, and I know how this cell reproduces. So I have the change of time, right? You know all that cells die over time. So I know how this cell behaves over time. And I can produce a differential equation or a calculus formula of how this cell behaves over time. Now, when you get sick, when you get a virus or a bacteria that infects the cells, so now I have an additional parameter saying my healthy cell time span is being affected by this new cell. And then I have to determine if this is going to be a direct proportion or an inverse proportion. And from there, I can see now how this virus is going to kill my cell over time. Will Amrita help students to improve his capabilities and skills? Of course. Amrita, we take such great pride in giving so much interaction time to our students. We want our students to come out at a professional level, that they're ready to take on any opportunities at companies. We have such a high placement at Amrita. Most of my students are all at internships right now. They're at Bosch, ENY, PwC, Intel, FireEye. I have a few students that are in Google right now. They're all over the place, and they're all using the skills that they developed at Amrita, this hands-on approach. It's not just about theory in a classroom. I can sit here and talk about mathematics theory all day long, but you don't get anything out of that. But at Amrita, we relate to that theory to the application, right? We show you how this drone can fly mathematically, then we'll go build it. Okay, we'll show you in our lab. We'll show you, for example, the Coimbatore campus, I believe, I don't know if it's still there, it's been a while since I visited, they have this F1 car that they developed. And we want you to have that approach. Our cybersecurity lab here at Amrita, we teach the students how to hack various problems Because if they know how to hack the problems, they know exactly how to stop the hack from happening. We have theory, real-world applications, solution. How mathematics is used in machine learning? I answered that question. Can you tell us about mathematics and computer science engineering? Well, the whole talk was about mathematics and computer science and engineering, right? For example, cryptography is an application of computer science, and they use number patterns to keep messages secure. In terms of engineering, all the problems in engineering, they have to be modeled mathematically. But every problem is different. My PhD was studying how to reduce turbulence over a plane wing. So what I did was I took a two-dimensional geometry of a wing, and I see how the fluid flow behaves over the wing. And what happens is over time, at different angles that the flow comes in, affects how this fluid flow behaves. So then I need in my equation the angle the fluid is coming, the velocity that the fluid is coming, and all of these different cases. So then I can report all my findings to an aviation company. And they can say, okay, well, if the fluid comes in this direction at this velocity, it's going to cause aerodynamic stall, which is going to cost more money for us. We want to avoid that from happening. But if you don't know, if you only know how to solve problems, and you don't know how they actually come into real world, then it will become a struggle. And that's really what you need to learn is how calculus works in the real world, where the exponential function comes from, why are complex numbers important, why all these concepts that you learn in school, they're important, how they're used in the real world to help people.
Due to time constraints, we might have to wind up the session for the day. I'm hoping most of the presenters got their queries cleared. We will come up with some more webinar sessions in the upcoming days. And officially, I thank you, Kurunandan sir, for this amazing session. And thank you all the participants for being part of this Amrita webinar. Thank you.
Thank you for giving me the time. Thank you.